All right, so when I teach alkane metathesis, Nobel Prize winning research, I think it's very important to know because it's actually used a lot in pharmaceutical chemistry. There's a lot of chemistry that we can't do without it. The big issue with alkane metathesis is that it quickly becomes a very complicated mixture of products. And because of this, it can be very daunting to keep track of what the products are. Now, there are special cases of this. If we do something where we claim one is in excess, typically ethylene, this pretty much means that only one of the alkanes we're working with is really like contributing to a mixture. But the reason we like to work with ethylene, C2H4, for alkane metathesis is that it pretty much guarantees is like a very short list of products. And the other is like ring opening, reclosing. So when we do ring opening, reclosing, we're either making or consuming ethylene to basically create one product. But let's say you're given a mixed alkane metathesis. So you're given equal amounts of two different alkanes. How do you figure out what the products are? And to do this, we're actually going to borrow from biology, and we're going to use a Punnett square. Now, with the Punnett square, we're going to take our alkanes. So let's say this is alkane A, alkane B, and we're going to write the fragments of each. And the fragments come from cutting the molecule in half. So we got the left fragment here, and the right fragment here, and I'm going to draw the squiggles here to indicate that we've cut the double bond. And for compound B, we've got the left and the right. So to figure out the first round of alkanes we make from alkane metathesis is we just start pairing things up. So in this case, we would connect the squiggles together, and we would get both the E and the Z forms. So if you end up with something that has the potential to be E and Z, you want to draw both. In this case, for the dimethyl groups on the same side and the ethyl group, we only end up with one form. In this case, we can have the two methyl groups cis, or we can have the two methyl groups trans. And again, with this one, it doesn't matter because left side is right side is symmetric. So the Punnett square here, I think, is the most efficient way for figuring out what your first pass of compounds are. What you do, take your alkanes, cut them down the center, top one, put the two fragments here, bottom one, put the two fragments here, and match them up. And again, you're going to have a mixture of the E and the Z forms for the cis and trans, depending on which ones you're working with, but you need to draw all of them. Now, this Punnett square method, I think, is the most efficient way of doing it. That said, there are a few assumptions being made here, and the first is that there's no self-metathesis. So what happens with self-metathesis is that this reacts with itself. So talk about that in the next video. But the other thing is that we assume the products don't react. So whatever we make here, these don't go on to react with themselves. And to figure out what that would be, you would have to do the different combinations of these within Punnett squares. So for this video, this is just kind of showing you how to do the first pass approximation. What happens if you get complicated issues like self-metathesis? Let's talk about that in the next video.